Good morning, everyone. Welcome to the Complex Materials session. My name is Miguel Nóbrega. I'm from the University of Minho in Portugal, and I'll be sharing the session with Professor Lagrangian from Manchester. Okay, so I will share this first part. Then, as you know, in the program, I have two talks, and I'll hand over the sharing of the session to Professor Young. So the first talk of the session will be given by Alexander Wikansky from the University of Cambridge, and he will talk about combined augmented Lagrangian regularization method for computing viscoplastic flows. Please, Alexander, the floor is yours.
Thank you very much. Yes, my name is Alexander Wikansky. I indeed live in Cambridge, UK, but I'm not from the university. I've been working in the CFD area for many years, and it's my current job title, but OpenFOAM is my hobby, so I deliberately didn't mention my current employer here. Right, and I'm going to talk about the viscoplastic flows, to be more precise about Bingham fluid. Let me briefly remind you what's that. If I, for example, plot shear stress as a function of shear rate, this curve corresponds to Newtonian fluid, and the tangent of this angle is called viscosity, so it's a ratio of the shear stress to shear rate. However, there are fluids such that even if the shear rate approaches zero, the stress doesn't approach zero, or other way around, if the stress is below some yield value, there is no shear in the material, so the material behaves as a solid. And if I draw this curve, I can say that the tangent of this angle is an effective viscosity, and here you can see the main difficulty associated with the Bingham fluid. I mean, if this point approaches zero, tangent of this angle becomes infinity. And it is why probably one of the most popular approaches in the modeling of viscoplastic fluids is so-called regularization. It means that the Bingham fluid behavior is replaced by another behavior such that at higher shear rate, it still behaves exactly as Bingham fluid. However, at this region, the shear stress approaches zero. It means that this angle, tangent of this angle is high, but not infinity. So there is a finite value of so-called effective viscosity. And probably one of the most popular models is by Papanastasiou. So there is this regularization function. At high shear rate, it is zero, right? So we have this region, and at low shear rate, it approaches 1, so it means that it's 0 divided by this 0 gives you some finite limit in this region. So it is convenient. However, this method has an uncontrollable error in this region, and it means that it doesn't tell us where exactly the transition from solid to liquid behavior happens, because according to this model, the deformation is everywhere. There is no solid behavior. It is why maybe 40 years ago, an exact method was proposed based on a variational principle. So let's consider only Stokes problem. This is a variational principle. This is a virtual dissipation by the viscosity. This is virtual dissipation by the plastic forces. And the main problem is this term is non-differentiable. So in order to avoid this difficulty, a dummy deformation rate was introduced, and you can consider as a constraint. So it demand that the dummy is equal to the real deformation rate, and we can take this constraint, multiply it by Lagrangian multiplier sigma, add to the variational principal. Then we take this constraint to power 2, multiply by some penalty parameter, add to the variational principal. And finally, since the flow is incompressible, we have an extra constraint, which is also multiplied by Lagrangian multiplier, and it is, of course, pressure. So in total, I have 2 Lagrangian multipliers, one is tensor, and a penalty parameter. So if I use extremality condition for this augmented Lagrangian, right, I can get 2 equations. One looks like Stokes equation. So basically, this is the total dissipative stress, and it's balanced by gradient of pressure. And the second equation basically links this dummy to the real deformation rate and to the Lagrangian multiplier. So I call this a second equation rheology equation because in the fully converged case, we remember this one is equal to this one. It means these 2 terms disappear. And then the meaning of this equation basically is that the sigma is nothing but the plastic stress. So in total, in fully converged case, we have plastic stress. This term disappears, and this is the viscous stress. This approach is exact, however, it's very slow, and I'm not aware of any 3D calculations made with this approach. So it's why I try to combine the regularization and Lagrangian, the augmented Lagrangian approach. So let's start again with the same variational principle. This equation, basically this term and this term are identical. You can verify it, right? So I take this term of this and add and subtract to this variational principle. So I don't change anything. However, if I do it and I rearrange the terms, this variational principle now looks like this. If you make the comparison, you can see instead of viscosity, I have the effective viscosity as Papanastasiou prescribed, right? And if I look at this term, the plastic dissipation, now it's multiplied by the regularization function. It means that this non-differentiable term is active only in a narrow region where the deformation rate is really low. So in the rest of the flow, I use the Papanastasiou model because there it doesn't introduce any error. So if I take this and I repeat the same calculations, I get again these 2 equations which are similar to the previous. So I have the this term is 0. I have the effective viscosity plus the new plastic stress, and I have the relation between plastic stress and dummy deformation rate, and so on. So in principle, I can try solving this equation, and I did it, and it's what I got. You see, this is a plastic stress, and it's called checkerboard phenomenon, right? And the nature of this behavior is well known because open form is a collocated method. It means that all variables are calculated in the centers of the cells. And if I want to write down the force balance for control volume, I need stress at the faces, right, separating the cells. So if I calculate this stress using an interpolation, I get a checkerboard phenomenon. We know it. It happens if we try to interpolate, for example, pressure gradient in a pressure correction equation. And the remedy to this problem is the same as in the pressure correction. It's called the Ricciao interpolation or Ricciao dissipation. It means that what I do, if I want to know the stress at this phase, I have to calculate the gradient of velocity first. So I calculate, of course, gradient of velocity in the cell centers. I interpolate it to the phase, and then I introduce this correction. So I subtract the normal component of the interpolated gradient and add this du dn. So this is the part of my code, and this term is calculated by the Sn grad function of OpenFOAM. Exactly as in pressure correction. So now we really can solve the equations. So for example, if I take simple solver, modify it, then okay, I solve the momentum equation. So the first line here, you can see in a fully converged case, it disappears. So it basically it is just for linearization, and it is calculated at the collocated grid. And the real stress balance is in the second line. I have the total stress, which is entirely calculated at the faces separating the cells. So I solve this equation, I make the pressure correction as in simple algorithm, and then I calculate everything at the face, effective viscosity, regularization, and so on and so on. Then I perform my rheology calculations to get the new value of stress. And probably, okay, let me go to the demonstration of the results. So probably one of the most classical test cases for this flows is lead-driven cavity. And you see this is the regularization function. I just remind you, in the liquid region, regularization is 0. And in the solid region, regularization should approach 1. And you can see it gives me the yielded and unyielded zones. So this white line is the region where the total stress is equal to the yield stress. It's not very nice because here I use interpolation several times to produce this line. However, it gives us the boundaries of the yielded and unyielded stress, similar to what, for example, regularization method would provide. And it is the plastic stress as calculated with the combined regularization and augmented Lagrangian approach, and you can see that indeed it is non-zero close to the boundaries of this region, and inside outside it is 0, because here the Papanastasiou makes a job. Now, as I said, the standard augmented Lagrangian is quite slow, and it's very difficult to get a 3D result with this method. So, and here I am calculating the same 3D cavity. It's only half of it, so this is the central plane. And here I use the pimple method. And the great advantage of pimple algorithm in OpenFOAM, it allows for the adaptive mesh refinement. And of course, in this case, the regularization function psi is a natural candidate for the criteria for the AMR, right? So I refine the mesh in the regions where psi is not 0 and not 1. So it is at the boundary. And if you look at these results, you can see indeed this is the coarse mesh. This is unyielded zone, right? This is a yielded zone, and the mesh is refined here, allowing me to resolve the interface between yielded and unyielded behavior. However, if we look at the supposed unyielded zone in the center of the cavity, you can see the same shape as in the two-case flow. However, if you look at the mesh, you can see there's mesh refinement everywhere. I would call this central region a numerical artifact. So basically, in 3D, this region, if I was using a regularization approach, I would get unyielded zone. But in the reality, it is not proper unyielded zone. There is always a slow deformation in this region. And just to demonstrate it differently, I plot the contours for the total stress, right? The yield stress in this case is square root of 2. Right, so square root of 2 is 1.414 times 2, something like this, right? So just slightly below, slightly above the yield stress. So if I take this threshold value just slightly above the yield stress, you see I have two boundaries between yielded and unyielded behavior. One which separates the bottom unyielded zone from this shear region, and second, this huge, allegedly unyielded zone in the center of my cavity. However, if I take the threshold slightly less, what happens? This one shrinks, and I say it is just a numerical artifact. It's really mesh dependent on my calculations. So, in other words, this region is quite funny from the point of view of plastic flow. It has a shape. You can detect it. However, this region is not a proper unyielded zone. Okay, so probably I approach the end of my presentation, so just some main points. So I combined the augmented Lagrangian method with regularization. For better performance, we can implement it in open form, but for the rheological part, we need a Richard style interpolation. Probably it's good for any type of rheology. It's always better to have stress at the faces rather than at the cell centers. The good side of the open form, it allows for adaptive mesh refinement. In this case, we have a clear candidate for the criteria for this. And yeah, I did some 3D simulations and with simple laptop, and I managed to get 3D results, and it's quite interesting from the point of view of the viscoplastic fluid mechanics. Yes, thank you.
Thank you. So it's time for questions. We have one.
Hello, thank you for your impressive work. Just a quick question, maybe I missed it during your presentation. I was wondering if your mesh adaptation algorithm is just geometrical or topological as well. While you actually refine the mesh, do you remove and add points, or you just have the points with the same connectivity, during during your simulation?
Well, I don't do anything special. I just use the standard.
Okay, sorry. So it is mesh refinement. So it is topological. Actually, you add points. You add points. Okay, I got it.
Yeah,
Thank
sure.
you.
I add points.
Thank you. Any other questions? Alexander, I have one. I'm not fully familiarized with the approach, but can you please elaborate more on the reasons related to the speed of the augmented Lagrangian approach, you mentioned? Why is it slow?
It's slow because this term is okay. Probably I go here. This term is non-differentiable, and to avoid it, we introduce an extra dummy variable, and for that dummy variable, we have this equation. The advantage of this part is that it's pointwise, so it's 1D equation, and although it's non-differentiable, it can be solved, right? And then you have this iteration procedure between this and this, between Stokes equation and the rheology part, and it really takes a lot of time. Now, if you introduce a regularization, you basically transfer a significant part of the plastic stress from this part to the usual viscose, right? So it means that now it is here, it is directly inside the Stokes equation, and it helps a lot in stabilizing the calculations.
Okay, perfect. Thank you. Any other questions? So if not, let's thank the speaker once again.
Thank you. Thank you.